Okay, so thanks again, Larry, for joining me and helping me work out this problem with you. So the first problem that we're going to focus on here is a gravitational problem. And the problem reads, consider the system below, which occurs on a planet that is different from the Earth. The planet has its own gravitational constant g and has no atmosphere. Suppose the angle theta is equal to 53 degrees. The coefficient of kinetic friction, mu k, is 0.25, and the mass m is accelerating down the plane at a constant rate of a. When the acceleration a is measured in units meters per second squared, its numerical value can be evaluated below. So a is actually the value from this integral. So it says, find the gravitational constant g with respect to this planet, rounding your answer to the nearest tenth. So we can actually solve this problem in two steps. The first step involves figuring out what this value a is from this integral. And then, of course, our second step will be to analyze this assembly and identify all forces acting on this mass. That way we can solve for g after we come up with some equations. So let's start with the first step. Okay, so our first step is to determine a. All right, so do you remember how to take an integral?
Yep.
All right, so let's write out the integral for a. So a is equal to our integral from 0 to pi over 2 of 4 sine of u du, all of that squared, and this is in meters per second squared. Okay, so to take this integral, the first thing we're going to need to do is we're going to need to calculate the integral of sine of u, right? So let's go ahead and do that, right? So if we do the integral from 0 to pi over 2 of 4 sine of u, right, what would this integral result in? This is pi over 2 here.
First, you could take out the 4. The first sine of u is going to be 0. And then, wait, no. The integral of sine is negative cosine.
Right. So we'll put negative 4 cosine.
Yeah.
And then we're evaluating this, right, from 0 to pi over 2.
Yeah.
Okay, good. So let's go ahead and do that. So we need cosine at pi over 2 and cosine at 0.
Cosine of pi over 2 is 0, and a cosine of 0 is 1. So it's going to evaluate to like 0 minus 1.
Right, so this is going to come out to be positive 4, right? Okay, so yeah, we have 4 as our result for the sign here. And of course we have to square this, so we're going to have a is equal to 4. We're going to have to square that, and this is going to come out to be 16. So our result here is 16 meters per second squared. Okay, so let's actually put this result down here. Then we can clear the board a little bit and start on step 2. Okay, so for step 2, what we're going to do is we're going to essentially analyze this system, and from there we're going to identify all forces acting on our mass, and that'll allow us to set up an equation and from that equation we can solve for g. So we're going to analyze the system and determine g. Okay, so let's start by drawing the system again. We're going to place our block over here. We have our angle theta down here. And according to the problem, our theta is equal to 53 degrees. Our friction coefficient is 0.25. Okay. Now, let's see here. Let's just underline all of this information down here. Right, and the problem also states that the planet has its own gravitational constant g and has no atmosphere. Right, so no atmosphere means we don't have to worry about air resistance. So let's start identifying all the forces acting on this block. So can you tell me a few forces that you can see?
The frictional force going upwards.
Right, so we have frictional force
It's going along.
up.
Yeah.
Mm-hmm. Okay.
You got the normal force to the plane.
Right, so we got normal force going up like this. We'll write that as F sub n.
And you got gravitational force going downwards.
Right, so we got gravitational force going down like this. And we'll write this as F sub g. So this is the weight of the block. Okay, so now that we know all of our forces, right, the next thing we need to do is to figure out a way to combine these forces together so that we can write some kind of meaningful equation. So what formulas or what equations do you know that allow us to combine forces together and essentially describe our system with?
Newton's second law.
Okay, so we're going to apply Newton's second law. Newton's second law, right? And the thing about Newton's second law is that Newton's second law applies in all directions. Now, if you look at the system that we have, if we're going to apply Newton's second law to the system, it's convenient for us if we create a coordinate axis that's aligned with this incline, right? So what we're going to do is we're going to create an x direction going this way. I'll represent our coordinate axis with a blue line. So we'll have the x direction going this way down the incline, right? And then we're going to draw the y direction. So y direction is going to be perpendicular to the incline. So it actually extends this way. Okay. And since we set up our coordinate axes like this, we can already see that two of the forces are aligned with those axes, right? So we have our normal force aligned with the y direction, whereas our our frictional force is aligned in the opposite direction of the x-axis, right? So it's going the negative x direction. So the only force remaining here that's sort of at an angle is our gravitational force. So what we need to do is we need to decompose this into both x and y directions. That way all of our forces are aligned along the axes, and then we can apply Newton's second law. So to do that, it helps to notice that we have an angle here between our gravitational force and the perpendicular y-axis, right? So the question is, how do we determine what this angle is?
Oh, it should be the same as the angle we already have. So
Yeah, right? So yeah, it should be the same as this angle.
yeah.
And we know it should be the same because if you were to sort of reduce the incline of this plane until it goes to 0, you'd see that the same thing would happen between our line for FG and our y-axis, right? So we can say that this theta here is the same as this theta here, right? Now, this means that we can now decompose FG into its x and y components. So we're going to say FG in the x direction. Right, we can find that by drawing a line from our y-axis parallel to the x direction until it intersects FG over here. So this will be our FGX. And then for FGY, we can draw another dashed line along the y-axis, right, until you've traveled the same y distance as FG, right? So let's just write FGX in blue over here. Sorry, FGY in blue over here. Right, and now all we need to do is we need to write an equation for both of these components. So let's start with FGX. What would FGX be from this diagram?
FG sine theta.
Right, FG sine theta. And we can see that because FGX is opposite to this angle. You can see a little right angle here, right? A right triangle. And FGX is opposite to this angle. So we can say FGX is equal to FG times sine of theta. Now, what about FGY?
FY cosine theta.
So you say FGY would be FG times this cosine angle here, right? So
FG.
cosine theta. Okay, good. So now we have all of our forces aligned along the coordinate axes. Now we can apply Newton's second law in both directions. Okay, so let's start with the x direction. So in the x direction, we can write our Newton's second law, which says the net force in the x direction is equal to the sum of all x forces in this diagram. Okay, so our first x direction force would be FGX. Right, so FGX is going in the positive direction of x. So this is going to be a positive value. We're going to write Fg, which is also mass times gravity. So we'll put Fg times sine of theta. And what's our next x direction force?
Friction force in the opposite direction.
Right, so friction force, it's going in the opposite direction, which means that it's negative. So this is going to be negative F sub F. And Newton's second law says that this must be equal to the mass of the object, right, m, multiplied by its acceleration. Right, so this is m times a. So this a is the acceleration along that incline, right? Okay, so far we know everything in this equation, right? We know the mass, we know the acceleration, we know the angle theta. The only thing we don't know here is our frictional force. And also, once we replace Fg with mass times g, we also don't know g, right? Which is the goal of this problem, to figure out what g is. So let's start first by rewriting this equation and substituting the proper values. So Fg would be m times g, sine of theta here. And now for our friction force, F sub F, we need to be able to determine this friction force from this diagram. Now, the thing is, there's actually a formula for friction force that we can use, right, in accordance with this diagram to help us get a better equation. Now, do you remember the formula for friction?
Is the kinetic frictional coefficient times the normal force.
Right, kinetic friction coefficient, which is mu k, times the normal force, F sub n, right? Now, how do we get this normal force here?
It's going to be Newton's second law, force times mass times acceleration.
Right, so we're going to apply Newton's second law. Only difference is, here we were applying it in the x direction, but now what we're going to do is apply it in the y direction to help us determine Fn, right? So we're going to say apply Newton's second law in y direction. All right, so along the y direction, Fn is going in the positive direction, so we're going to say F net in the y direction is equal to Fn. And we have the y component of Fg, right, going downwards. So this would be minus Fg cosine of theta. So m times g cosine theta. Now, do we have any acceleration along the y direction?
No.
All right, so no acceleration, so this is going to be equal to 0. Right, so this equation tells us that our normal force must be equal to mg cosine theta. So let's go ahead and write that down. We have normal force equals mg cosine theta. And now that we have this result, we can substitute it here. That way we have an equation for our frictional force. So our frictional force is going to be friction coefficient multiplied by mg cosine theta. Right? And all of this would be equal to ma. Okay, so we're almost done with this problem. The only thing left is to sort of work this out, cancel out some like terms, and solve for g, right? So let's start by canceling out the m's. And the next thing we're going to do is we're going to factor out the g from both of these terms. Okay, so we're going to write g multiplied by sine of theta minus mu k cosine of theta is equal to a, which means that our g value is equal to a divided by sine minus mu k times cosine. Okay, so all we have to do now is just substitute all of these values into this equation, and that'll give us our value for g. So a is 16. All of our angles are 53, so we're going to have sine of 53. Kinetic coefficient is 0.25. And then our cosine is of 53 degrees as well, so let's go ahead and substitute this into the calculator, see what we get. Okay, so what's the answer that you got?
24.7, because it's put in there.
Okay, so same here. And it said to round your answer to the nearest tenth, so
Yeah.
we're going to have 24.7 meters per second squared. All right, good. So did you have any questions about this problem?
No, you explained, you broke it down well.
All right, cool. Okay, so yeah, let's move on to the second problem here.